Bismillah ar-Rahman ar-Rahim, and welcome to lecture number 13 for basic engineering mechanics. In this lecture we would continue our discussion about moments, and we would discuss something which is called the moment about an axis. So in our previous lecture we discussed how we can calculate the moment of a force about any given point, but now we want to calculate the moment of that given force about any axis. And then we will look at some more examples of how we can use this concept in real life. So what is the moment of a force along an axis? So we are concerned about the turning effect of our force, not the complete turning effect, but only the turning effect of that force which produces a rotation about a particular axis. So here, like we see in this example, so we are applying a force F on this wrench to open this nut from the wheel, but we are only interested in the turning effect of our force which tries to unscrew this nut. Of course, this force would produce a turning effect which would try to rotate this nut in other directions also, but we are not interested in that rotation. We are only interested in the turning effect which is trying to open up this nut. So the scalar definition of moment of a force along an axis, or the scalar form of the formula, is simply given by the moment of a force about an axis is the force itself times the perpendicular distance from the axis. So this looks very similar to our formula for moment of a force around a point, about a point, but in this case, rather than using the distance, the perpendicular distance from that point, we are more interested in using the distance, perpendicular distance, not from the point but from the axis from where we want to calculate the moment of force. Okay, so in this case we see that rather than using so let's me clarify what I mean. So in this case we want to apply this this formula, that moment of a force about an axis is force times the displacement, the perpendicular distance from that axis. So we are interested to find the moment of this force about this z axis, about this y axis, because this is the axis of interest for us, because when the screw would when we are opening the screw, we are so the rotation that we are interested is along the y axis to open this screw. So we want to find the moment of the perpendicular distance from this force to the axis, the perpendicular distance. So in this case we can see that if we were to find the moment of this force about the point O, we would be using this distance which is given as r. This is the distance from the force to the origin point O, the perpendicular distance from the point of action of force to the point O. But in this case, because we are trying to find the moment of a force about an axis, so we would rather be using this length. So this is the perpendicular distance from this axis, and because this axis is the y axis, so our formula would become the force times the perpendicular distance from the y axis. Okay, so if this angle is theta as it is shown here, then we can simply say that and this length is d, so this smaller length would just be equal to d times cos of theta, because this angle is going to be theta, so this angle is also going to be equal to theta. So let me just mark a few things so to make it more clear. So I can draw that for you. So this vector is vector r, and so this distance is d from here to here. Okay, let me just make it a little bigger. So this distance is d, but this is not the distance that we want. The distance, to use this formula, we want the perpendicular distance from the axis. So this is our y-axis and we want the perpendicular distance from that axis. So we are interested in this distance. Okay, so we are interested in this length here. Okay, and this length, as I have stated earlier, so this length is just d cos of theta, because this angle is theta. So the moment of this force F about the axis, y-axis, is just equal to F times d cos of theta. So that is how we use the scalar analysis form for the moment of a force about an axis. Okay, so moving on, now we want to discuss the moment of a force about an axis in its vector form. So if we're using vector analysis, so first of all, the first step is to find the moment of the force about any point on that axis. So the step number one is that I choose any point on this axis, y-axis, and on that point, using that point, I find the moment of this force F about that point. Okay, and the next step is, so that's the first step, we use the formula that moment of the force about the point O is equal to R cross F, where R is the position vector and F is the force. Okay, but now the next step is to calculate the moment of the force about an axis. Is we use this moment, which was moment of the force about a point O, and then we dot it with the unit vector along that axis. So this gives us the moment of the force along that axis, and this gives us a scalar. This is not going to be a vector, this is a scalar, and all of these are vectors, because when we take the dot product of two vectors, the result is not a vector, but the result is a scalar. Okay, so to summarize all of the results that are given here, we can say that the moment of a force along an axis, that the scalar form of that moment is given by UA, which is the unit vector along that axis, dotted with the position vector R cross F. F is the force. And so this, when we simplify, we plug in the values, we know that, and whenever we do a cross product, we can always represent a cross product using this form, where we have I hat, j hat, k hat on the top, and then rx, ry, rz, and fx, fy, fc. But when we do this dot product, there is an easier form to write it down. We can, this whole thing can be considered as one determinant of a matrix, and the first term of that matrix is just the elements of this vector UA, UAX, UAY, UAZ. The second term in this matrix is just Rx, Ry, Rz, and the third term is Fx, Fy, Fc. So this is how we would analyze, how we would find the moment of the force about an axis using vector analysis. Just to summarize everything that we have said so far, so moment of a force about an axis is the turning effect that force produces not around a point but about a particular axis. And to find that moment, there are a couple of things that we have to, a couple of ways we can find that moment. First is by using vector analysis, or rather the first method that we studied today was that of scalar analysis, and that basically states that moment of a force about an axis is just the force times the distance from that axis. And the second method that we studied was the moment of a force about an axis using vector formulation, and that is where we looked at this formula. So where the moment of a force about a point about an axis A is just the unit vector of that axis dotted with the position vector cross F. And mind you, this position vector can be taken about any point which lies on this axis. So we have some leeway on choosing this point, and the result would always be the same as we would see in the examples. Okay, so here we look at the first example for today. So this example, so we have multiple forces acting on this block, and so we want to find the resultant moment about all of the three axes, the x-axis, the y-axis and the z-axis. And we would like to use the method that we have studied so far to find the resultant moments. Okay, so let's start with finding the resultant moments around the x-axis. Okay, so we know that resultant moment is just sum of all the individual moments, and this is true for a moment about a point, and this is true for moment about an axis. So we start off by finding the moment about the x-axis. So let's write it down. So the moment about the x-axis due to all of these three forces. So let's start with this force F1, and this force is being applied here, but we want to find the moment of this force about this x-axis. So we look at the line of action of this force. So let me just draw a line. So this force is being acted along this line, and the distance, the perpendicular distance of this force from the x-axis is actually this distance here, and I can call this as so this is the distance, and this distance is 2 feet. So the contribution to the moment of this force about the x-axis is going to be equal to 60 pounds times 2 feet. And I have a positive sign here because the moment produced by this force is counterclockwise, and we already assume that counterclockwise moments are considered to be positive. Now we look at the second force F2. Again, the perpendicular distance of this force F2 from the x-axis is just this 2 feet. To understand why this is going to be 2 feet, we can draw the line of action of this force like we did before, and we see that the line of action of this force is acting downwards, vertically downwards, and so the perpendicular distance is going to be this distance I am trying to draw in blue. So this is going to be this line from here to here, and as we can see that this distance is going to be equal to 2 feet. So the contribution of this force to the moment along the x-axis is going to be equal to 50 pounds times 2 feet. Now we look at this third force, which is a 40-pound force, and this force is already acting along the x-axis. So any force which acts along a direction, that force will not produce any moments in that direction. We can simply, it's very easy to see why that should be the case, because we saw that moment of a force about an axis is just equal to UA dotted with R cross F. and we saw that so whenever we do a cross product, the vector cross product of R class F is going to be perpendicular to both of these components, and if UA is in the direction of F, that means that this dot product is going to be equal to 0. So we have no contribution from this third force. So this is the total moment due to these three forces along the x-axis. So next up we look at the moment along the y-axis, and so the moments along the y-axis are equal to again we look at each force one by one. Again, this force F1 is acting along the y-axis, so this will not produce any moments along the y-axis. This F2 will produce a moment along the y-axis, and the distance from the y-axis is 3 feet, because if we extend this y-axis backwards, which I'll do for you, so if we were to extend this y-axis in the other direction, I should probably change the color. So this, I have extended the y-axis in the negative y direction, and so this is going to be my distance from the y-axis, which is 3 feet. So we can say that moment of this 50-pound force is going to be equal to, and this force, this moment is going to be in the negative direction, and this is going to have a negative sign because this is producing a clockwise moment. So I can say that this is equal to minus 50 pounds times 3 feet. So, and there was a zero contribution from this force F1. So now we look at this force F3. Again, we want to find the perpendicular distance of F3 from the y-axis, and which is just going to be equal to this distance. I can choose some other color, so let's choose this color, and so this is the distance for that we are looking at, and so that distance is going to be equal to 40. So this is going to be equal to 40 pounds times 2 feet, and the third term is going to be equal to 0. So now we look at the third term, mz. Again, by the similar argument, F2 is going to produce no moments along the z-axis, but F3 is going to produce a moment, and the distance for F3 is going to be equal to 2 feet, and this is again producing a clockwise moment. So I can say this is equal to minus 40 pounds times 2 feet, and this force is acting along. So this force is the line of action of this force passes through the z-axis, so this force will not produce any moments along the z-axis. So we have only one term for the moment of these three forces along the z-axis. The three key points to notice here is that we have to take care about the moments, the distances, and we also have to take care about the signs. Moments can either be positive, which means that they are producing clockwise moments, and moments can either be negative, which means that they are producing counterclockwise moments. Okay, so let's get rid of everything, and so here I have attached the results. As we have already discussed the moment of the forces of moments along the x-axis, we have these two terms. For the y-axis we have these two terms, and for the z-axis we have just this one term. Okay, let's look at this next example where we want to find the moment MAB produced by this force F along the AB axis. So we have this force of 300 newtons which is acting at this point C, and this is acting vertically downwards, and we want to find the moment of this force along this AB line. So the axis of the moment that we want to find is this axis. Let me draw the axis. We want to find the moment along this axis. Okay, and so we already know the formula. Let's see how it is applied. So we know that the moment, so the moment of this force about an axis, and we are only concerned about the magnitude of the moment, and this magnitude is going to be equal to the unit vector from A to B, and we cross it with, we dot it with the position vector cross F. Okay, so let's write down what these things are in this equation. So what is our position vector? So the easiest thing is to just write the force, and the force in this case is going to be equal to minus 300, and we have a k hat vector. So because this force is acting vertically downwards, we have an axis, so we get that the force is equal to minus 300 k hat, and I'm not putting in the units here, but it is understood that we are dealing in newtons. So next thing we want to measure, we want to write the r vector, and to simplify our life, we know that we can use any position vector along the action of the line of action of the force. So let me just use that to make our life easy. We know that the line of action of this force is this line from this point A all the way downwards. So normally, if we did not know about this school way, we would have been using this vector, but rather than using this vector AC, we can simply just use this vector, which I'm going to draw. So we can use this vector. Okay, and because we saw that the moments produced, to find the moment I can use any position vector along the line of action of that force, and this vector is much easier to write down. This vector, let me also give a name to this point. So this is A, B, C, and let's just call it D. So RAD is very easily written as 0.6, and this is I hat. Okay, so I know two of the three things I need to use this formula, and the third thing is just to find the unit vector along AB. And so what is this unit vector going to be? We know that the y component of this vector is 0.4, so let me just write it down. So the x component is 0.4, so 0.4 I hat plus 0.2 j hat, and then we divide by the magnitude of this vector to make it a unit vector. So this is the unit vector along AB, this is the force vector, and this is the position vector from point A to point D, which is along the line of action of the force. So this turns out to be equal to 1 divided by 0.447 times this vector, which is 0.4 I hat plus 0.2 j hat. So I can plug in all of these three numbers into this definition of moments, and to do that I'm going to erase this part, so that I have some space to work with. So I can just write UAB here so that we remember that UAB. So my moment is just equal to the determinant of this vector 0.4, 0.20, and so next comes R, so which is equal to 0.600, and then we get 0, minus 300, and then we have this magnitude here. Let me just make space for that, and we have 0.447. okay, and just is just trivial math from here on, which is 0.447, and this determinant is going to be equal to, the only non-zero term is going to be equal to 0.2 times plus 0.6 times minus 300. So when we solve this determinant, this is the only non-zero term that we get, and I hope you can just plug in the values here and you can get the magnitude of this moment along the axis AB. But if we are careful enough, we can see that the question asks us for the moment vector AB, because this is capital this is bold, in bold, so the moment AB vector is just the magnitude times the unit vector, which is just UAB, and we already know what value of the UAB is. Just to separate everything that we have done, and we just draw a line here and a line here. So this is the value of the unit vector, and this is the moment. I hope the basic concepts are clear, that how do we use the vector form of the moment along an axis, and how do we use the scalar form. Okay, so here we look at the solution. First of all, we find the unit vector as we did just now, and then we find the position vector and the force vector, and then we plug it in all of these numbers in, and we get this result. Okay, and again, to find the vector, we use the magnitude times the unit vector, and we get the result here again. Okay, so we have a few more examples in these lecture slides, and they use the same concepts that we have already defined, and the only two concepts here is how do we find the moments about an axis using the scalar analysis and using the vector analysis. So we would solve the later examples during our online class. So that is it for today. Assalamu alaikum wa rahmatullahi wa barakatuh.